let me introduce you first. Maude is a PhD candidate working at the Argelander Institut for Radio Astronomy at the University of Bonn at the submillimeter group. She has a bachelor in fundamental physics from Paris. I don't know what the XY is. I don't remember my numerals. Okay, university. And a master's of astrophysics from Strasbourg University. And it's also Maude is also a member of Astronomie on Tap Bonn. So whoever has been to our live events at Fiddlers has seen Maude there. And today we will talk about, this is your research, right? This is what you are investigating.
Yes, exactly.
In your research. So let's start with your presentation, and we'll go along. Please start.
Thank you for the introduction. So I guess the first thing you might ask yourself is, what is this Sunyaev-Zeldovich effect? What is this name? Where does it come from? Because it's not very intuitive, let's say. So this name actually comes from the two scientists who predicted it. So those scientists are Rashid Sunyaev here and Sunyaev-Zeldovich here. So they were both Russian scientists. And Rashid Sunyaev was actually the PhD student of Sunyaev-Zeldovich. So, of course, because he was his PhD student, he was getting instruction and he was being guided by Sunyaev-Zeldovich on what to do, what to investigate. And together they predicted the effect in 1969, which is quite some time ago, actually.
That's fantastic. The same year that we sent humans to the moon, to land on the moon. Fantastic.
Yeah, that's actually right. Yeah. Okay, so you might wonder now, what is this Sunyaev-Zeldovich effect? So actually, it's a collection of effects. There is many flavors, let's say, of the SZ effect, but they are all based on the fact that the photons, which are the light particles, can have their energy modified by the presence of galaxy clusters. So their energy might change when they go through galaxy clusters. Now you might ask yourself, but what are galaxy clusters? So it's a group of galaxies, of plenty of galaxies. Actually, it can contain around 100 to 1,000 of galaxies. So it's quite huge. It's actually the biggest, the largest gravitationally bound structure in the universe. So they are bound together, all those galaxies, by gravities, and they are the largest structures that work that way, actually. So here you have, for example, a schematic of a galaxy cluster, and on the right here you have a real image of a galaxy cluster, so you can see many galaxies.
So all these galaxies belong to the same unit, right? To the same cluster, the ones we see on the right in the image.
Yeah, exactly, yes. So they are all part of this big group of galaxies that we call galaxy cluster. And as a... Oh, sorry, go on, yeah.
No, I was just gonna say, just to remind to people from home that galaxies are made up of hundreds of billions of stars, right?
Yes, absolutely. Yeah.
So this cluster contains a lot of information, right?
Oh yeah, a lot of sun, a lot of stars. Not all of the stars are like the sun, but a lot of stars, a lot of planets also probably, a lot of gas. It's very complex physics in happening inside. Yes. I can give you an example of a group of galaxies to sort of give you an idea. So maybe you know that our galaxy, the Milky Way, is actually in a group of galaxies and other objects. This group is called the local group. And for example, you have also Andromeda Galaxy, which is part of our local group. So yeah, we are also ourselves part of a galaxy cluster, sort of. So as I was telling you, this SZ effect is about photons, the light particle, having their energy modified by the presence of galaxy cluster in the universe. But it's not any photon, actually. It's the photons coming from the cosmic microwave background. So we speak about SZ effect only when those photons coming from the cosmic microwave background have their energy modified by galaxy cluster. But maybe you might wonder, what is the cosmic microwave background?
We do. Please tell us.
Yeah, to put that in maybe a very small sentence and very clear, we could say that it's the first light of our universe, sort of, which is quite amazing. To get into more detail about how that happened and what it is exactly, I'm going to guide you a bit around the history of our universe. You can see here an image with like all the history of our universe as we see it today. So as you may know, there was a big bang at the very beginning, and then an inflation phase where we say that the universe became very big in a very small amount of time. 10 to the power minus 32 seconds. So it's really, really fast. And only 1 second after the Big Bang, actually, we were left with a dense soup, a dense plasma with plenty of particles inside. So photons that are the light particles, electrons, quark, a big soup of particles, very dense and very hot. What happened to the light particle at that moment is what I want to show you with a small video. So imagine that those orange points are the electrons. Actually, at the beginning of the universe, it was so dense, there were much more electrons than there is on this very small simulation. But just to give you an idea of what is happening exactly, if we have a photon inside this very hot and very dense plasma, what is going to happen is that the photon is going to scatter on the electron. So as you can see, it's getting absorbed by an electron, by an orange ball, and getting emitted in another direction, in a totally different direction. So as you can see, it sort of stays trapped. It cannot really escape because each time it's going to try to move, it's going to hit one of those electrons. So what happens is that all the photons present in this hot gas are getting absorbed by the electrons. So they're sort of trapped. They cannot really escape this dense gas. To give you an example in numbers, so 1 second after the Big Bang, in this very dense gas, photon can travel only 10 to the power minus 10 meters, which is roughly the size of an atom, before they get absorbed by an electron. So they can barely move, actually. And because of that, we say that the universe was opaque. No light could really escape. It was dark, basically. For example, nowadays, photons can travel 10 to the power minus 6 meters before they interact with something else.
Wow. So, that is not, there's not much space they have there. They're really trapped, right?
Yeah.
So we cannot see them.
Exactly.
That's the point, yes. And what changes?
Yeah, so there were no lights because they were trapped by the electron. But what happened is that the universe, which is expanding, so the gas, when a gas is expanding, then it cools down. And it's exactly what happened with the universe. The primordial plasma gas gets cooled down because of the expansion. And at some point, it's cool enough for atoms to form. And you might know that atoms are composed of the nucleus and the electrons. So all the electrons that were before going freely around and absorbing the photons, they are now trapped with the nucleus inside an atom. And at that time, the photons do not scatter on the electron anymore. They're not trapped anymore. They can escape. And at that time, we say that the universe became transparent because for the very first time, light was able to escape this dense soup that was the universe before. So that happened actually 380,000 years after the Big Bang, so quite a long time ago. We call this epoch reionization, and the very first light that was able to escape the very first light of our universe is this cosmic microwave background that we see here, for example. So this image is an image of the cosmic microwave background, so of the very first light of our universe. And you may recognize this looks exactly like the Earth being projecting onto a flat 2D map. So it's usually a sphere, but you project it and it looks like that. And what you might see is that there is some region that are more red, so where there is more temperature, because what this map represents is the fluctuation of the temperature at the time light was able to escape for the very first time. So you can see regions where there were more light, more energy, and more particles when it was denser than other parts of the universe, which is absolutely amazing, because then you have a map of how the structure of the universe was at the very beginning, actually.
That is fantastic. You talked a bit about temperature. Is the universe hot at that moment, and how does it compare to earlier epochs before it became visible to us?
Yes, so the universe was at the beginning, of course, extremely hot. By the way, physicians have trouble really explaining what was hot at the time of the Big Bang. Mm-hmm. And then, of course, with expansion, it cooled down. I'm not sure exactly the number, the temperature of the CMB at the time of emission, but of course, it was much hotter than it is nowadays.
Mm-hmm, mm-hmm. Some easy numbers. Okay, because I did a presentation on that and I have them in my mind just for our audience. It's around 2,800 Celsius. So the temperature that we understand in Europe. And before the universe, when we were talking about this, before atoms started forming, it's millions of degrees. And now it's minus 270 Celsius now in the current universe. So there's a big difference of how it cooled. Please continue. Sorry.
No problem. Thank you for the numbers. Yeah, I think that's really nice to have them. So, yeah, to go back to this Sunyaev-Zeldovich effect, it's the fact that the CMB photons get their energy modified when they pass through galaxy clusters. But you might ask, like, how does that happen? So the CMB occurs very far away in the past, 380,000 years after the Big Bang. So it's quite far away from us. But those photons that were emitted at that time, they're still present nowadays. And when they reach us, when we measure them on Earth with telescopes, they have gone through all the universe. And sometimes they've gone through structures, as you could imagine on a picture like that. And sometimes they pass through galaxy cluster. And in galaxy cluster, there is very hot gas, and then they're going to interact with this hot gas and gain energy and have their energy modified. So that's what is the SZ effect, actually.
So they get more energetic, right?
Yes.
They steal the energy from the electrons they interact with. Good.
yeah, we could say that, exactly.
Yeah.
It's a very good image, yes. Yes. So there is, as I told you at the beginning, different type of SZ effects. But what I might told you is that all of those Sunyaev-Zeldovich effects are actually very small. Actually, I've heard that Zeldovich did not want to publish the paper because he thought we would never be able to do science with them because they're so small. He thought they would never be detected even. But that's not the case today with our telescopes that are very powerful. We are able to see it and to deduce plenty of things from it. So that's really interesting. I'm going to mention two effects that are really easy to explain. So the thermal SZ effect and the kinematic SZ effect. You can see that the thermal SZ effect is around 100 microkelvin. So it's really, really small. It's 110 to minus 6 Kelvin, and the kinematic SZ is even smaller. To give you a comparative example, as Eleni said it very well, the CMB temperature nowadays is 2 Kelvin, which is roughly minus 273 degrees Celsius.
I got it right.
Yes, yeah. And you have to imagine it's 10 to the power minus 6 smaller than that. And of course, the CMB photons are still present in our universe and they are dominating. So those effects are under those very, very hot, very cold, but actually much hotter than those effect photons. Yeah. Okay, so let's give you an explanation of this thermal SZ effect. Now you have everything to understand it. So as I told you, the CMB was emitted very far away in the past, 380,000 years after the Big Bang, and the photons from this very first light, they travel through the universe, and while traveling, they lose energy. But sometimes they pass through galaxy cluster, and in galaxy cluster there is very hot ionized gas. So a bit like at the beginning of the universe, there is free electrons moving around, and so those photons that are very cold, they're going to scatter on those very hot electrons. We say inverse Compton scatter. So what happens is that you have a low energy photon coming from the CMB that is going to meet a very high energetic photon. And it's going, as Eleni said it very well, it's going to steal the energy from the electrons, basically. So you're going to obtain a high energetic photons and a low energetic electrons. And what happens is that then those CMB photons have more energy than they should, and they're going to reach us on Earth when we can measure them. So what happened exactly is that because we have this relation between the energy and the frequency, so the energy is just a constant multiplied by the frequency. So when you have a high energy, you have also a high frequency. So as I told you, the CMB photons are supposed to be very low energy, very low frequency. But when they go through galaxy cluster, they gain energy. So they have higher frequency than they should. So when we observe the sky, and especially the CMB at different frequencies, as you can see here, for example, 44 gigahertz or 545 gigahertz, we're going to see a deficit here in blue, so less photons at low frequency, because the CMB photons that were supposed to be here when there is a galaxy cluster, they have gained energy, so there is less photon than it should, and more photons at high energy. They have been moved, sort of, and that is the thermal SZ effect. You can see here, for example, in terms of a curve, so at low frequency, when you look at the CMB at the spot of a galaxy cluster, you have less photons at low frequency than you should and more photons at high frequency than you should. Because of that, you can actually, when looking at the sky, you can pinpoint and count where are the galaxy cluster because of this effect. So it's quite amazing.
So you can trace in the sky the galaxy clusters. So that's also a good tool. Another way to find galaxy clusters in the sky, right? Oh, fantastic.
Yeah, exactly, yes. Basically, as we already said, thanks to this thermal SZ effect, so the fact that the CMB photons that are cold gain energy on the very hot electrons, we can count galaxy cluster, which is very interesting for astrophysics, of course.
Is this very common for the photons coming from the CMB? Does it happen to all of the photons? Or
no,
some?
It's actually very little, yes. You're doing very well to mention it. Yeah.
So it's a very small percent, but yet we can detect the clusters through that because the difference is so big in the energy they steal. Oh, wow. That's an amazing effect.
Yeah, it is. Yeah, I mean, I like it at least.
And to imagine that who was Sunyaev, that he didn't want to publish it.
It's actually a very famous effect in astrophysics, and it's growing a lot because the telescopes are now getting so precise that we are actually able to measure those effects very well and understand them and use them for cosmology, but also for astrophysics. So it's really something that is only getting more and more used. Yeah.
Good. Please continue.
Yeah. So the last effect I want to talk to you about is the kinematic SZ effect, which is actually the effect I'm working on for my PhD. So it's going to be very simple. It's pretty much the same idea as the thermal SZ effect. So it's the photons coming from the CMB that scatter on the electrons. But this time, it's not only the hot electrons. So it's not only the electrons that are very hot, that have a lot of energy. It's all the electrons that are undergoing the motion of the cluster, all the electrons that are moving, because you have to imagine those galaxy clusters, they're not fixed. There is velocities inside of them. They're moving in the universe, and those electrons are also going under this motion. They're also moving, and so this effect occurs when the CMB photons scatter on the electrons that have a motion. And what is interesting about this effect is that with that, you can gain some information on the velocity of the cluster, because the effect is actually proportional to the velocity itself, the velocity of the electron. So that's a really interesting effect also for astrophysics and cosmology.
Good. That is a very interesting effect, and apparently it's a very useful tool to understand our universe. Is that correct?
Yes, absolutely, yes.
So let's add Anna to this conversation.
Well, yes, that effect has been useful. I mean, it's going to be more useful because the sensitivity is better, but it is the instrument that has allowed us to detect the most galaxy clusters, confirmed galaxy clusters. So even since the long time, we knew around hundreds of galaxy clusters around 20 years ago. And then SPT came and gave us around South Pole Telescope gave us around 2,000 clusters. And then we got similar with Planck, which is a space mission. But where we are now is we expect to detect 10,000 of galaxy clusters. So we are going one level above, But it's the biggest tool that you have to detect them.
That is fantastic. And I think you had some input on something we discussed with Maude that I already forgot because the beer is getting into my brain very fast, faster than the CMB photos are coming. Cheers! Faster than the CMB photons are coming to us, of course. So please elaborate on the question.
What we were discussing. Yes. We were... I just got confused. So Maude was saying that the energy change is so high that, that's why we detected. But really it's not that the energy is so high because, the change is very small. If you see the difference in the Kelvin, in the temperature, 10 to the minus 6 is like 0.0000006 or 1. Yeah. So it's more about it's such a specific pattern, right? So imagine that you always have the same shadow, right? It's exactly the same shadow. So you can always detect this shift if you know exactly how that's going to look, right? You can predict that at every step that is so specific, this must be this specific effect. It's nothing else.
So it has a characteristic signature and you're looking for that in the data and this is how you find it.
Yeah, so Maude introduced a beautiful graph showing this curve pattern. So that's the change in intensity. And we tend to cheat on this. Usually you show a proper CMB body, spectrum. So a black body, proper Gaussian curve kind of idea. And then you show that eventually, if you see it through a galaxy cluster, you will see a dent on this curve. And we exaggerate it always, we show such a big difference. But in reality, if you will plot both of them properly, one on top of the other, you will not even see it.
Okay, so it's a tiny effect, but it's very useful to detect more clusters. So it's more useful tool to detect clusters of galaxies, right? Maybe for our viewers, how many galaxies do these clusters have? We said they're made of galaxies. Maybe Maude or Anna can tell us how many galaxies these clusters have?
Yeah, around 100, 1,000 usually.
Okay, wow, that's a big collection. That's a big collection. And I wanted to ask, so we said it's important, although a small effect. It was predicted I will go back to this question later, but I want to ask first, why is it a good tool to understand the universe through the Z effect? How do we understand the universe by using this effect?
Yeah, so thanks to the effect, we can sort of see galaxy cluster, which allows us to understand like the structure of the universe, because as some of you may know, there is this cosmic web structure, which looks a bit like a neural network of the universe itself. And where there is galaxy cluster, it's very dense. So you can, by tracing galaxy cluster, you can trace the structure of the universe too. And with the structure, you can sort of deduce like how could that structure have occurred in the first place, have happened, and that gives you some information on how the universe property might be actually.
So the structure is made out of galaxies, right? And then we can trace that. Yes, please, Anna.
No, just going to comment about the structure part, right? Like you have filaments in between, but if you can detect these two, and other studies have shown also, like through optical light and visible light that we're used to when we observe galaxies, we see that until certain separation of these two, you could trace, or galaxy clusters, you could trace some filaments, some gas in between them. At some point, it's too large the separation, you cannot really trace it, and sometimes it's too close that you cannot differentiate what's a filament and what's really a galaxy cluster. But there are some ranges where you can see this, and that's the gas that Maude was introducing. And she's actually the one that works with that effect more than me.
Great. I'm jealous. I don't know more about this effect, so you can enlighten me. Please, Maude, sorry to interrupt.
No problem.
But if I may say, like, you can see that Maude is really in the cosmology part, right? And she will tell you all about like counting clusters and like how they're important, and they tell you all these little tiny parameters that measure what really our universe is, right? So we go and measure every little thing, and we say, oh, in this direction is this, in this direction is that, and all those parameters describe what we know. But galaxy clusters are actually objects that you can use as astrophysical labs, and that's the part I will tell you, because I don't do as much cosmology, but if you observe with the Sunyaev-Zeldovich effect, you observe actually something that is proportional to the pressure. You could convert it on that. So you can use this effect also to study what really is happening inside the clusters. How do they form as objects? So not only using them as tools, but to understand this for objects that are just forming.
So you can use them for the larger scales, which is the large-scale structure, the skeleton of our universe, basically. Right. And you can also use it for what is inside the skeleton to understand the marrow bone. That is great.
You can do very precise astrophysics, measure temperature, mass, and everything with it. So,
And I think Anna mentioned that you can understand what the universe is made of, these small parameters. So we can you tell us a bit more on that, a little bit?
Yeah, so basically with the different flavor of the SZ effect, you can constrain cosmological parameters, different cosmological parameters. For example, with the kinematic SZ effect, because you probe the velocity of the cluster, you also probe the velocity of the structure themselves. And there is a parameter called the growth of structure, which measures how the structure grows, how fast, and everything. And you can get that through the SZ effect, which is very interesting for cosmology.
Can we use it to get the ingredients for our universe? What it is made of, how it is evolving. So this is what we're talking, right?
Yes, but I wouldn't say so. On that, I'm not 100% sure, but I don't think you can constrain all of the parameters with only this effect.
So you can use it with other effects to constrain better the parameters. Okay.
Yeah. So for those of us who follow us on AOT, you, Eleni, gave a talk about the cosmology, right, and how this works. And what I remember is that you also say we use different probes to measure this, right? So it's like if we go and measure the table and we say, okay, I measure it with a ruler, I measure it with my hand, right? And eventually you want to get the best measurement you can, right? So it's the same for these parameters. And galaxy clusters, because it's just now when we really can use them, it's what they're bringing is real certainty to know. So like they're reducing the errors of what we already knew. So if you imagine the example of the table, you say, oh, before I measure the table to be 10 centimeters, plus or minus like 3 fingers. Because I don't know how much is that.
Or with beer bottoms.
Exactly, or with beer. But eventually you go and say, well, actually those 3 centimeters, like, these 3 fingers mean this much centimeters. And you can combine all the results. And then you say, well, I have something that is so specific that I can know so well the properties that then I can use it to really reduce the errors in this. So instead of going plus or minus 3 centimeters, you go 0.5 centimeters, for example. And then you really know what the table is made of, or in this case, the universe for us.
That is a very good point. And thank you for this example of everyday life, so we can understand the different effect of measurements and how we can improve our measurements. I have so many questions for you guys. I'm really interested in this effect. I had this question before from Maude's presentation, and it stuck into my brain. They predicted the effect from physics, right? So we're talking about physics here in 1969. So my question is when it was confirmed through observations, when it was the first observation, and with what instrument, telescope, that made us understand that, okay, this is the Z effect, and we will call it a Z effect,
Yeah. I'm not too sure exactly of the date or anything, but I think that was much later. Yeah. I don't know if Anna knows more about that, maybe.
For the detection of the Z effect? I will say that's early 2000s, probably. So I work with Apex set data, which is a survey, and it was the first targeted survey to observe with this effect. And that was performed between 2000 and 2007. Before that, there were observations because we knew about the effect, but really specific. So, for example, there are big clusters that we knew existed from other observations. So we went there and we said, okay, yeah, we really can see it. But there was never anything before 2000 about having a sample or having a lot of observations about this.
Okay, so it became big survey after Apex, right? Apex is a radio telescope?
Apex is a radio telescope in Chile, and it observes in millimeter wavelengths. And then at some point, there was this big project in the US called South Pole Telescope, which I think has been presented here a couple of times. And they wanted to test the instrument that they were going to put there to detect these galaxy clusters, to detect this effect. So they created a small instrument to test it, and it was put in Apex, which was the telescope in Chile, to test it. And that's how we actually been evolving through this. So it's kind of been every step of the time, which it happens with every telescope, right? You test it, you see what it goes better, then you move it to the next one. And that was in 2000, but now we are South Pole Telescope is SPT, and that was SPT1, and now we are going for generation 4 of, updates on.
Wow. It sounds like a PlayStation.
It kind of does.
I'm joking. So this is the future. We're talking about dedicated surveys now with so these are telescopes on the ground, right?
It's very hard to do in the ground because, in order to observe it across the whole spectrum, you need to observe at really high altitudes in order to avoid the humidity, and in order to get the biggest spatial space that you can find in the atmosphere, to get this observation. And Maude is working on that, actually. That's a future project that is coming. But before that, the best observations we got were from space. Because since this effect is so small, the noise from the atmosphere, so to observe it and to skip all this vapor column that we have between the atmosphere and us is very hard. And once you do that, to really model all that noise, it's like when you take a picture and it's humid outside and you can see it almost in your picture. Well, it's the same idea, in a way. You take this picture and we have to remove all these. And since the effect is so sensible, you have to be so careful with this. So Earth is great, space is amazing, it's a ideal situation.
Yeah. But the problem of space is really, it's much more expensive, and that's why it doesn't happen as much as we would like it to happen. But Yeah, the telescope, some of us are building now, especially Germany and US, Canada, CCAT Prime is going to be built in Chile at 5,600 meters, which is very high in altitude, in a desert, because that's the place where there is very little vapor in the atmosphere, because that's really dry. And it's mostly sunny every day, very low rain and very dry atmosphere. So that would probably provide very good measurements.
That's correct. We have a question actually from.
No, wait. I will go to the questions from the chat, but I'm being very selfish here. I will admit it. I want to know more, so I will go through my questions first. Okay. I wanted to make to ask for a clarification. You said from space. Is it space balloons or is a telescope outside Earth's atmosphere, like Chandra, for example, the ones we used? You said sorry, Anna. You said we observe.
No,
we can observe.
Yes. I was just waiting for Maude to answer. No, there were some experiments with the space balloons, but the observations are with the Planck mission, and Planck was a satellite located at L2 for those astronomers who know what that means, but just located in a very good spot in the space that actually allow us to observe the whole sky multiple times, and it observed around 6 rounds with a full coverage between frequencies of 30 gigahertz to 600 gigahertz. So and a lot of little lines of this spectrum that we already know how it works, so we could really cover it at different specific points.
Great. Planck was the one that also confirmed the cosmic microwave background and got better detections on these fluctuations that Maude was referring to before, right? Yes.
Yeah, that's exactly right. The image I showed is from Planck. The very first satellite was Kobe, but they had very low resolution, let's say, so they couldn't observe like very tiny fluctuation. Then the US sent WMAP, which did better than Kobe, and finally Europe came in with Planck, which did the most precise measurement to this day of the fluctuation of the cosmic microwave background, yes, of the temperature fluctuation.
Yeah.
I mean, in a way, you can see it as, when you go to the doctor for eye doctor and they test you for glasses, and you start seeing all blurry things.
Yeah.
I think we kind of went on that way. We were blind and we had an idea, and we went with Kobe, and then we saw, and it's when you see the letters, and instead of seeing an A and a B and a C, you see a smush. But you're like, oh, it's like letters. And then you went one step further, you're like, oh, I see the A, but not really the B and C. Or no, the shadow that they produce, and then we've been going every little step to see it, to focus and see it properly.
I hope you don't reach a point where you don't understand the difference, because when I go to the eye doctor, this is what happens to me. He tells me, is this better or this? I'm like, it's the same.
In a way, that's actually what happened with the work we do, right? And why our work is so important to be precise and correct is, you go and you already have the definition, but you start, I don't know if it's the previous one was better or this one was better, And when we correct for our images, as I was saying, right, you want to remove all that noise that you observe, you might end up in that, and you might end up playing a little bit with just putting filters, the same as you do Instagram with your pictures, just that kind of idea, or like distinguishing is this better or the other, by just using basic mathematics, using basic statistics, and assuming a lot of things. This effect and this goes with a lot of assumptions of how the object's supposed to behave, like how the galaxy clusters behave, how they're formed, are they all, stable, are they actually crossing one another, things like that.
Okay, so I have 2 questions from my list and another 2 from the live chat. Well, actually, there are 3 questions from my list. We'll put them together. Okay, so I wanted to ask if we can, again, I think the beer is working. Okay. How can we combine the AZ measurements with other data? And if we do it and why we do it. And in the background, you can hear my son screaming. And okay. And if this provides some further information about galaxy clusters, there's the space between galaxies within the clusters and the galaxies in the clusters. I think that was also a question from the live chat, if we can get information about the galaxies themselves. A big question.
Do you want to go ahead, Maude? You want me to go?
Well, I haven't done much of that myself, but I know you usually combine SZ with X-ray to get some temperature measurements. So, yeah, it's totally something we do, yes.
Yeah. I think, the most common that we combine is with X-ray, as Maude said. This is a bit technical, but when you observe X-rays are biased towards the more dense clusters just by the way the emission in X-rays happens. So by the physics that happens, it tends to be more biased towards like the fat clusters, so to say. So combining...
Don't be judgmental.
I'm not judgmental. I love fat clusters. They're easy to detect. But combining that with SZ allows us, for example, to have a big picture of what's the actual distribution of the clusters in the space, right? So we don't go only seeing the big ones, but we can obtain more information. And, again, this goes important for cosmology, for example. Another thing is that one big assumption we tend to do when we observe with this effect is we assume the temperature of the cluster. And usually that comes from X-ray observations. Nowadays, and we have a colleague, Jens Erler, he actually did a work where he showed that combining a lot of these observations will help us create like an upper limit of what the temperatures for clusters could be. So now we're getting into the point that we have so many observations, we really can get statistical information like these ones to settle better how the clusters behave. But
so if you have more information about the clusters themselves from another probe, which is the X-rays, then you can use the Z effect to trace other properties. So that's why you use the combination, really, right?
Yeah. It's also because the X-rays are emitted by the intracluster medium, right? So it's the gas or like the plasma that is around the galaxies, and so the X-ray and the SZ are observing the same thing, right? So it's like if you take an X-ray of your body, but you take an MRI, you see different things, right? One sees the bones, the other ones might see tissue. So it's the same. It's kind of difficult if we take optical observations where we can see the galaxies and the stars, because they're giving us information about other objects inside this soup of a set, of like these galaxy clusters.
And can you get information about the individual galaxies within these clusters through the Z effect? Or is it only, we said you can trace clusters of galaxies. Can you get any information about the galaxies themselves?
Not really. Mm-hmm. So I guess technically, yes, the galaxies could produce the effect, right? So they could interact with the photons background, but the effect will be so small that we don't detect it. So, one thing is what you were asking before, where like you say, do a lot of photons interact with these objects, right? And it's not that many. The difference is we have a lot of galaxy cluster, right? Like it's a big area, thousands of galaxies in a space with a gas, right? But if you reduce that by 1,000 and you put it in a small galaxy, then your chances of the photons interacting with the right electrons and getting to us, reduces.
Okay, so before I find this question from the live chat that I lost somewhere in the chat, I want to ask you if there are simulations of the Z effects and what they tell us and how we can use them, if you know. And if you don't know, there you go. Thank you very much, Sandra, our savior. And then if you don't know that, I will ask you what Sandra just posted.
There are simulations. Yes, there are different ways of simulation. So Maude and Jens, Maude probably will explain this part, but they work on creating like sky models of like how will affect what we observe, and they model all these things that we know how they're supposed to behave. As in, if you put particles like in what we usually see cosmology particles, you put boxes and they start evolving and eventually they create a galaxy. Usually we don't see the SZ effect on those. Mostly because they get painted at some point, so to say. So instead of letting all those particles evolve until that point, because it's so expensive for the computers to do all these calculations, we take assumptions and we say, well, we already know these effects happens. It always happens like this. So let's put this information here and see. Then we use those simulations more to understand how to use SZ as a tool than as as an observation to understand the galaxy clusters.
Yes, so it's important and a very useful tool nowadays that we have better computers to get us faster to understanding the effects in our data, right?
And Maude can tell you all about that one.
Oh, yes, great.
Yeah, it's really important actually. So I've been working on 2 simulations. So one of them is what we call hydrodynamical simulation. So in that case, there is actually particles, baryons, so matter particles that evolve, and there is actually physics that is put inside those simulations. So equation that tells, okay, how should those particles behave? How should they collapse together to form structures? And how should they interact to produce effects like the Z effect, for example? And this simulation, the magnetical simulation that I've been running a bit, I didn't made it myself. It was done by Klaus Dolag and his team in Munich. And it's running on a supercomputer also in Munich. And it's one of the most, in the top 10 of the most powerful computer in the world. And I can tell you to run it on like a 7 by 7 degree or 40 by 40 degree patch, which is quite small because the sky is way much bigger than that. It takes a week of full supercomputer computation, which is a lot because those simulations produce a lot of particles in a big box. Then they need to let it evolve to form structure. They need to inject physics in it, physical meaning, and then yes, you can produce a map of how the SZ effect will look like in real life. Mm-hmm. But it's just a patch. It's not even a full sky map. And then you can get, as Hannah explained it, some simulations that are dark matter only. So in that case, it's also particle in a box, but there is no baryons. It's only dark matter, which basically gives you like the potential where the structure are going to fall, collapse, and form. But then, because there is no real matter, you need to paint it on it. We say that way in astrophysics. So you need to say, okay, if there is this big dark matter potential, then it would correspond to a structure looking like that in physics. So then you need to inject on top of those simulations sort of how it would look like in real life. So there is simulation, yes. It's really non-trivial to do. Mm-hmm.
And if you make a mistake at the beginning, before you press enter, you lost a week, eh?
Yeah.
At least.
Yeah. Well,
no one has done that ever. No one. No one has made a mistake. No one.
Yeah, well, you can stop it, but the worst is really when you launch it and you let it run for a week. And then you realize, oh, I didn't run the right parameter or something. Then, yes, you really lost a week.
There is a question. Well, there are 2. I think my favorite question today was if you can detect UFOs with the Zeg effect. And I would say yes.
I wish.
As a non-expert, I will say yes. Okay, I think the question that I had misunderstood was if you can detect individual galaxies with a Z effect and not clusters of galaxies, because you said you can use it for big, like hundreds and thousands of galaxies. So if you can find individual galaxies, let's say they don't belong to a cluster, can you use it, or is it not? No.
No, not really.
It's not sensitive enough.
The effect will be too small for us to detect it.
Yeah, our telescopes are not sensitive enough to get this effect from the galaxies.
But related to that question before, you were saying how how do we know if 2 galaxies are in the same cluster? What observations we use? And SZ cannot do that. But again, this all goes combined, right? So we have SZ that shows us the gas, the intracluster medium. We have optical data that shows the stars, the actual galaxies, X-rays that also tell us about the intracluster medium, this gas in between, and you can have infrared. And infrared gives information about the stars, that are being born, or the galaxies, the different galaxies. And using this information, you actually can calculate something that is called like the clustering parameter. So you can use different things to measure like how far are the galaxies and what is really a range where you say, well, if I extend my arms this far and I touch someone, is that my friend and lives inside my own house, or is someone else, So you really use all physics and all the tools that we have to study these objects to get to know, to get to say their galaxy clusters, to get to say which galaxies. And some people go and study each of these galaxies in detail, right? Usually there are one old galaxy in the center and a lot of small ones around it that are not as active. But people go and, focus only on those objects because each of these little things is kind of their own universe, and I think that's kind of important sometimes for the audience to follow, that so many things and so many details in every intrinsic thing we do, and it's hard to to cover all that with just one effect or one observation.
Yes, it's very important to combine observations, different tools, different wavelengths, different intensities and sensitivities in order to understand our universe, because there are different effects, right?
Yeah.
And that's what we learn from all this. And for me, it's amazing how theoretical astrophysicists can predict something 40 years before we managed to do it on a large scale. It's amazing, and it shows the understanding of the human brain of physics, and then how, by developing tools, we manage to make it an observation and study it in detail.
As for UFO question, I think
Yes.
it will have to be a very fast and hot UFO.
Great. Thank you. Yes, very, very nice, very nice. And plasma, right? Because
Plasma.
this is what,
Ionized UFO.
ion. Okay, yes, that's very important. So, guys, we can detect UFOs under certain conditions. They're plasma, hot, right?
Yeah,
and fast.
And fast, yeah. There
And
you go.
fast. There you go. Very nice. Fantastic. I would like to thank you so much for this fantastic conversation. I think we learned a lot. I learned a lot. Now I am a fan of the Z effect,
Good.
for sure, because I think the potential for future discoveries are very big, and that is very important. And now we have two tools and future telescopes that will give us better understanding.
2021, wait for it.
2021, it's going to be our year.
Yeah.